Hi. Okay, hi everyone. Niv Haim, and we'll talk about adversarial examples today. So let me tell you a short story. So I download this image of a pig from the internet, and I fed it into some any classifier like ResNet. You are familiar with ResNet? Cool. So ResNet told me that trained on ImageNet told me that there is a 98% chance there is a pig in this image. Okay. Then I added this kind of small noise. So this is much smaller than what you see. It's actually magnified by 50 times. I added to this image, and then this made this image look like that. Sorry, I don't think that you can see any difference in this image. But now when I fed it into the classifier, he told me that there is 99% chance that this is an airliner. And actually, when I asked it how much confidence it has that there is a pig in this image, so that's how confident it was having a pig in this image. Okay. So one note about this example. So this is not a random noise. It was specifically crafted to make this example look like that. Yeah. And this example was shown by these fellows back in the days, and they were the first ones to kind of like speak about the notion of adversarial examples in modern machine learning neural networks. Okay, so let's start with some definition. What is an adversarial example? And let's use the term coined from the paper by Segedi. So let's just read it together. So we find that applying an imperceptible non-random perturbation to a test image. Okay, so it's a non-random perturbation. It is possible to arbitrarily change the network's prediction, and we term the so perturbed examples adversarial examples. Okay, so two things. These are not random noise, and it must be small enough that it will be imperceptible for human people.
And this works with any image, not just pig.
Not with, sorry?
Not just with a pig.
Yeah, you can basically do it with, obviously it depends on the network, but basically you could make these examples to be, I would make like a guess, which is probably true for any neural network. You can find these kind of noises almost for any image, and you can make it change the label or make it the label that you wish. So I specifically wanted this image to look like an airplane here, but you can do this for any neural network. And okay, so the topic of adversarial example is fairly broad, so there's like really a lot of things to say about it. But in this class, we will focus on one and probably the most popular notion of adversarial examples, which is perturbation attacks. So that's exactly what is written here. We want to find some like to tweak the image just slightly and to change the label. Okay, so the outline of the class today. So we will see adversarial examples. Check. We will learn how to generate them, and we will learn how to defend against adversarial examples, or actually maybe defend against adversarial examples. And we will see some cool properties and advantages. Okay, so let's talk about how you generate adversarial examples. And let's do a brief recap on how we train neural networks. So you take a bunch of images, your data set, and you are feeding it to some architecture, some neural network, and you want to make this neural network as good as possible. Let's call this neural network F with parameters theta. And you define some loss function over the outputs of the model on some given image and the true label. Okay, and the purpose of the loss is to kind of say how well we classify it, how well this classifier is actually doing its job, right? So this is the most common loss. So, right, just to be on the same page, you are familiar with this loss, percent loss. This is like the most common one, which connects the predictions of the model with the labels. Cool. And while training the model, we want to minimize the loss. So how do we do that usually? So probably more than one way to do it, but the most common one is just by following the gradient. So the gradient descent is like the most common way to train classifiers today. And by following this negative direction of the gradient, we hope that the classifier will be better at classifying images. Okay, so now when we want to generate an adversarial example, we have the model, but now it is trained. We're not going to change the parameters anymore, so we're just going to discard this. We're not going to change data at all. And now we're going to take some image. So this is another pig, it's an 89% pig in this case. And we want to somehow fool the classifier into thinking this is something else. By changing delta, right? So we are talking about perturbation attacks, so we're going to add small perturbation delta in order for the prediction of this model to be different than the true label Y. Okay, so how are we going to do this? We need to somehow find a way to measure the badness, how bad the model behaves given the predictions and the true label Y. So here is a suggestion. So we used L for training the model. We use this loss to maximize how well the classifier is at classifying. Maybe we can use the same loss function, but now to maximize the badness, how bad it acts on this image. Okay, so what we're going to do, we're going to try to fool the classifier by maximizing the loss over X with respect to delta. So the only thing that we are going to change now is delta. Again, you are probably used to thinking in the like changing the parameters of the model. So the data set is fixed, and you have the model, you have the parameters, and you're going to change the parameters in order to make the model better. Now the model is fixed, the parameters are fixed, and we get some image. Again, the only variable in our optimization problem is this delta, which we want to change in order to fool the classifier, to change the label. Cool. So how are we going to do that? Yeah.
You assume that you know the loss. Just to train them.
Okay, it's a good question. If I assume that I know the loss function, well, you could probably use different losses. This is like the most common way to generate samples. I'm sure it would also work for other losses. And yeah, I mean, in general, if you know that this is a classifier, so you could, even if you don't know that it was trained with gross entropy loss, even though I don't believe that there are any classifiers these days that are trained in any other loss, but you know, there are like other classification losses in general. You could maybe use others. So yeah, I mean, the answer is like probably it was trained with this, but you could also probably use some other loss function to find this. This is just one way to do it. Okay, cool. So how are we going to do that? Again, by solving optimization problem like we always do, we're going to follow the gradient of the loss, but this time with respect to delta. And now we're going to maximize the loss, right? So before we use the minus of the gradient because we want to minimize the loss. Now we're going to follow the positive direction because we want to maximize. Yeah, okay, so these are two things. Cool. Yeah.
If you want to, let's say you want to make a pig into an airplane, you need to follow a certain, like you need to shove it into an airplane, not only the badness.
Right. That's also it's a good question. Actually, I didn't expect you to speak about it, but since you've asked, so you could kind of like choose this Y here. So instead of like maximizing with respect to the true label, you can kind of like minimize with respect to some specific label, which is exactly what I did previously. And then this is just a optimization problem. So right, so you just define your loss, and the variables are going to be delta, and you just solve this optimization problem. Yeah, that's good question. Cool. Okay, so some small technical remark, because we're going to use it for the next part of the class. I'm going to say, instead of taking the gradient with respect to delta, taking the gradient with respect to x, where x is just the input to the model. This is usually the way you will see it in the literature. You'll see like following the gradient with respect to the x, where x is the input. And this is exactly the same. So this is equivalent, right? So if you want to see this, so you can think of the input to the model as this like summing fixed x, which is some image, with delta that is being changed. This is how I presented it to you now. But I could just equivalently just discard all this and tell you I'm going to feed some x image x and then change it. So x is now like a variable they can change, and it is initialized with some image. And then at any point during this optimization problem, you can just stop and say, okay, how far this x went from the beginning, and you call this thing delta, and this is exactly the same, right? So from now on, we're going to use delta taking the gradient with respect to x. So this is that technicality. Yeah.
Shouldn't this be constrained so that delta doesn't become, for instance, an image of an airplane?
Yeah, okay, that's another good question, and we will see this in a moment. So, but this is like kind of like we're building the intuition on how to even find such an example. So this is a suggestion. We have the loss that we use to measure how good our classifier is, and now we're going to change the role of the loss to measure how bad the classifier is. And the way we are going to try and find these examples is by following this positive gradient with respect to the input. And so now delta is going to be just this, right? So we're going to just add this direction, and let's see what it does. Okay, so this is our original image. And okay, we have the model, of course, like it's somewhere like behind the scene. We have the ResNet 50, and we take the gradient with respect to x, and we add this to the image. And what do we see here? So first of all, we see that you can barely see any difference. So the gradient in this case was quite small. And it also changed the original label. So from 90% pig, now it became like 68% hay. You could argue this is like a real example because there's hay in the image. Okay, so maybe not, I don't know. Let's try, let's take more steps in this direction of the gradient. So here, this image where I added 10 times the gradient with respect to x. So now you could clearly see the image has changed. And the label, well, in this case, didn't change, but it changed the probability. Okay, and if I take one more step, not one, 100 times, then I managed to find some image which pull the classifier to thinking that this is FireGuard. FireGuard, I don't know if you know what FireGuard. I didn't know what it was. It's like a FireGuard. Yeah, I have an image later in the slides. Okay, so we thought this is not a FireGuard, but we can clearly see that this is a pig as humans. By the way, if you take 1,000 steps in the direction of the gradients, then you will get 99% spotlight. Okay, so did we generate an adversarial example? You think?
Yeah.
Okay, no, of course, that's a okay question. Right, this was the adversarial example. We need delta to be small. So how are we going to do this? So we want small noise. So we have x, we have delta, we want it to be small. What is small delta? So again, we're going to use one definition for smallness. And we are going to bound delta with some norm. We're going to use the infinity norm. And this is how we're going to define our smallness, by saying that the infinity norm of delta must be smaller than some epsilon. Let me just stress what it means, if you're not all of you familiar with infinity norm. So, for example, what is an example of, so delta is going to be some vector, or it's like an image, but you don't really care about the shape of it. It's basically just like a vector that you put it in lines. And how does a vector with infinity norm smaller than 0.1, how does it look like? What is this thing? So this is some, you can have many values, but any values must not be larger than 0.1. So it can have many values, but it must be between 0.1 and minus 0.1. So here's some examples that can be in this kind of like such small deltas. Yeah, okay. But for example, we cannot have this. So we cannot have this kind of value. This would defy our definition of boundedness by 0.1. So we will not have this kind of values. Okay. Any question about infinity norm? Why is it called infinity? Again, I did. Okay, this nice story, and we have time today. This was originally planned for 55 minutes, but we have 2 hours. Then believe me, you don't want to be in the class where I tell it in 45 minutes. So this is like the notion of norms. So we have like, you're probably familiar with your vector. You're familiar with the 2 norm, right? Which is just taking the sum over vi to the square, then just put it at the square. But this can be generalized to p in general. So the p norm to the power of p would just be this. And if you take p, so the most common norms are either 2 that you are familiar, the Euclidean norm. There's 1, which is Manhattan distance norm, if you're familiar with that. And the next one, which is the most famous one, popular one, is infinity. So if you take p to be like I don't know, infinity, like very, very large. So this would, and of course you need this is important, right? So you have like these positive numbers, which goes to infinity. And if p is very large, then from all these sums, the most prominent one would be the maximal one. So it just means what is the maximal over all p. So this is just infinity norm. So if the maximal value of the vector must be bounded, it means that, right? So all the values must be between this bound and the minus. Yeah. Yeah. Cool. So we have 2 notions. We want to follow the gradient, but okay.
Sorry.
Yeah.
But why do we allow it to be minus value?
Why do we allow it? Because this is belong to this definition. So if my vector is bounded, like infinity bounded by 0.1, it means that it can have negative values, but not larger than 0.1.
So it's only the definition of what we want the vector to be.
It's a definition of bound. So we need to somehow define smallness, and the way we're going to define smallness is by this infinity bound. It's not the only way. It's just one way to do it, the most common one. That's why we're talking about it here. But this is the way to bound your delta. So if epsilon is very small, so you take epsilon to be 0.00001, then you're gonna end up with some vector which like this delta is going to have like values which are really, really small. If you add it to your image, you will not be able to see it. But you can control how small it is by changing epsilon. So if epsilon is very large, you allow delta to have very large perturbations. But if we force delta to have like epsilon, like infinity bound with small epsilon, then we force delta to be small. This is the notion, this is how we define smallness. Again, it's not the only way to do it, but that's a way to do it. So how can we combine these 2 notions of following the gradient with respect to x, as we saw that it can change the label, but also requiring that the delta would be small. Okay, so we kind of like enforce this gradient to be bounded with infinity norm of epsilon. So we have x, we want to follow the gradient, so this is going to be delta. But now, okay, the gradient to be anything, it does not have to be bounded at all. But now we're going to take the sign of it. So each value here is either -1 or 1, or maybe 0, but probably we will not have any 0 in this. And we're going to multiply this vector by epsilon. And for any gradient with respect to x, we manage to kind of tweak it into a new vector, a new delta, which is bounded by infinity norm of epsilon. But this is clear why this is infinity, this is bounded vector. Cool. So great success. And okay, so this method, probably again like one of the first methods to generate adversarial examples is called the fast gradient sign method, or FGSM. You're gonna see it many times if you're gonna end up reading some adversarial examples literature. So this is good to know. Okay, questions about? Yeah.
So why would you want to like multiply it with epsilon?
Because
About like the ratio.
so if you take the sign, then you're gonna end up with a vector which is bounded by infinity norm of 1.
Yeah, but why would you want to take the sign?
Okay, so right. Okay. There are too many answers to these questions. Well, first, intuitively, it gives you some delta, which is somehow related to the gradient with respect to x. So this is why it's good. And it's also bounded. So you can control how far you allow to change your image by adding this delta. Why specifically this sign? Because it's like the simplest case. Okay, and also there's a good reason that was, I think it was not discussed in the original paper, but you could actually think about this delta as maximizing the first order expansion of the loss. So say we have the loss, right, that we used before, and we want to find delta, which change, or I don't know, somehow maximize this loss over all possible deltas which are bounded by infinity norm epsilon. And this is in general, you need to somehow solve this. But what you can do, you can expand this Taylor expansion. So you're gonna have like this term, like the 0 order, and the first order gonna end up like this. So this is right rate delta. And if you solve this optimization problem, so this has like a closed form solution. It's like actually a nice exercise if you want. Then you will end up with the delta that maximizes this thing here, this is we don't care about, that is bounded, then I end up with this. So this is another like answer why do we take this. You can look at it from two ways, with like the intuitive way or actually this. Yeah.
If one of the gradients is smaller than epsilon, so you might ruin the maximization. No?
If one of the okay, so right. Thank you so for asking this question. It's not exactly okay. So your question was Yuval. So Yuval said, okay, but if one of the values in the gradient was not smaller than epsilon, so we're going to like ruin the direction, which is true. We're going to end up with something which is not in the direction of the original gradient. Nevertheless, this is one way to do it. And if you want like a formal intuition why it's okay, because it maximizes the linear the approximation of the loss. Cool. Okay, so let's see how it looks like in reality. So here's an example on MNIST dataset. So here are some examples, and I trained the classifier to solve MNIST dataset. So it's a very simple classifier, like 2 convolutional layers and 2 linear layers. And when I fed it to my classifier, it was mostly correct on all of them. So there was like 1 error here, predicted 2, but this is actually 3. And now let's generate adversarial examples for this classifier on this dataset, right? So what we're gonna do, we're going to take so the adversarial example. We're gonna take for each image in the test set, or for example for these ones, these 4 over there, we're going to add this delta that we just discussed before. This is how it's gonna look like for this classifier. And this is what we're gonna get. So these are the images we're gonna end up with. Then we can feed it back to the classifier and see if we manage to fool it. And actually, in this case, we did not. We were not able to fool it, so we still left with 4. But still, like for quite a lot of images, we managed to find an adversarial examples that can fool the classifier by adding very small noise. Okay, so the test order in this case was 98% on the clean test set, and then some measure you could think of like how robust my classifier is. You can take the test set, the clean test set, generate adversarial examples, or maybe adversarial examples, like attack the test set. So each image you're gonna generate a new image, and then ask now what is the accuracy on this new set. So do you have like a guess how much the FGSM error was in this classifier? Yeah, okay, right. So about 50%, actually 40%. Okay. You see that by you see that by this very simple attack on the classifier, we managed to decrease the accuracy from 98%, which looks like very good classifier, to 40%, which is not so good. Now I have to tell you about the epsilon. In this example, the epsilon was 0.1, and you could argue if this is maybe too large, too small. So again, this is some intuition, and in general, you would want epsilon to be large, but not too large, because if epsilon goes to be like too large, then you can basically change each image to go to any other image, and that's it, and then it's not interesting. Okay, question. Yeah.
Does by test error mean accuracy?
Yes, it's yeah, thanks. I have to fix this slide. Yeah. It's not error, it's accuracy. It's the same. 1 minus. Okay. Great. So this is FGSM, which is a simple attack. It's very fast. This is like why it's called fast, and vicious because it can kill your classifier very quickly. And you can look up in these sources. I put everything here if you are willing to learn someone. Cool. So what can we do to defend against such attacks? And it is. You already say okay.
If you don't publish your network, it's harder for them to generate adversarial examples, maybe.
Okay. Right. So, sorry, the name? David. So David said, okay, if they didn't publish the model, then it would be harder for me to generate the examples because I cannot generate gradients, right? That's somewhat true. We were gonna talk about black box examples where you don't know the model, but this is true. But maybe something else.
You want to incorporate into your loss function,
Okay.
you need to be robust.
Cool. Okay, so that's what we kind of like going to do. Maybe we can take these new samples and feed them back into our training set, and in this way make our model more robust to these kind of like changes. So this is called adversarial training, which is again probably the most common way to try and defend or to robustify your model. So let me repeat what we're gonna do. We're going to generate. So this is okay. I actually did samples from the test set, but now think as if they were like in your training set. So we're gonna have like our training set, and we're going to generate adversarial samples while training. We'll end up with images like that, and now I can like ask my loss function to classify this to be the real label, like 4. Or I want to like this one to be 3, etc., etc. Okay, cool. So, yeah.
Why do these things work? Like, what is adversarial examples exploiting the system that makes it work?
Let me get to this. I have some slides giving like some intuition about why it works. Unfortunately, the question is a bit. Wait for the slides. Okay, wait. So I want to stress something about adversarial example, adversarial training, that many people kind of miss the first time they hear this. It's not that we are at the end of the training, we're gonna generate adversarial examples and then train one more step. This is not what we're going to do. We're going to feed this in like during training. We're gonna take a batch, like batch of clean images, generate adversarial examples, right, with DL4CV. We're gonna end up with this, and we're going to feed this back into the model. All together with that, doesn't matter, like you feed both of them or just the adversarial examples. And you're gonna train, and then you're going to make a step to change your parameters to make it like better at classifying clean images and classifying adversarial images. And now we're in the next step of our training, but data 2. So we're gonna again get some batch of images, and we're going to generate adversarial examples for this new model. And this is important because these new adversarial samples may not be the same as the ones before. So as you change your parameters for the model, you're going to end up with maybe different adversarial examples. And this is how adversarial training works. So this is kind of like augmentation during the training. And you train it to be more robust. Cool. So let's see some numbers. So for standard training, we had this test accuracy 98% and FGSM accuracy 40%, right? So you remember what it means? We take the test set, we make examples, and we check how accurate our model is, and this is how it was. But now we have our adversarially trained model using FGSM, and the test accuracy was slightly less, but still quite well, 97%. But if you look at the robust accuracy, we managed to make it much better than before. So now, if you take your more robust model and you generate adversarial examples, this is how accurate your model is going to be, and this is quite an improvement. Yeah.
Are there other techniques of like filtering the adversarial images?
What do you mean by filtering?
Like averaging, like masking?
So I'm not sure if this is your question, but maybe it is related to that. So like, did we actually solve the problem? So maybe you mean what happened to like the 6% that we still managed to get fooled by? Or
No, I mean,
yeah.
If I will take a mask and average the image, like blur it, would it?
So again, I'm like trying to take your question, like you are asking if there are other ways to defend from adversarial examples, and you suggest by averaging stuff like that. So
I also asked if the adversarial image is robust. Yes, so like if I change the bits.
Okay, it is okay. So these are all good questions about them, like giving some intuition about it. So I have some slides giving some intuition about it. But in general, okay, so this is not the only way to defend against adversarial examples. And also, like, the question is like, okay, so did we solve the problem? Yeah.
Did people do any studying about how much training is needed versus the size of the images? Because this is pretty small. I don't know. If
Yes. Okay. I'm gonna touch about real models, real data set later. Also, yeah. Good questions. Okay, so cool. So we saw how to attack with GSM. We learned about the research training, and okay, maybe this is the moment that you all been waiting. So let's get some intuition about like visual intuition on adversarial examples and adversarial training. So this is very simplifying the world example. You take your images. Images are in general like high dimensional objects. For example, MNIST are 28 by 28 pixels, so it's like 784 dimensions. But let's think, just for the sake of getting some intuition, let's think of them as our image dots in 2D space. So how would it be? How would it look like to find adversarial examples? In this case, we're looking for this delta to change these images, which is bounded in some box. Okay, that's another intuition on norms. If you look on the like epsilon box around some vector, so if it's going to be like a 1 norm, it's going to look like a diamond, and if it's like a 2 norm, gonna look like an epsilon box with 2 norm, gonna be like just a circle. Right? Like if you allow deltas which are bounded by norm 2 to be as not larger than epsilon, you're gonna have like a temple or sphere. And for infinity norm, you're gonna end up with this like a square, which looks like that. So these are all perturbations that are bounded by infinity norm, not larger than epsilon, where epsilon is like this. Okay. Cool. So this is how we're gonna look like for all the images. And so for doing FGSM, how would it look like? So we have our image in the, let's put it in the middle, and we're going to make just one step with the delta that we found. Here it is. We're going to end up over there, and we can ask ourselves, so this is going to be possible adversarial example found by FGSM. Just to see if you're still all with me, that's actually a wrong visualization. The dot should be lying on either one of the corners or here, right? Because we take the sign, so we actually throw it. That's actually just like a tip for you if you want. It's good to like try to visualize stuff because you actually learn something in the way. So when I first built this slide, I didn't notice it, and then like, okay, this is actually wrong. Because when you take your gradient, which could be anything, and then you take the sign, think of your gradient without any zeros in the middle, so just complicated stuff, and it could be anything, and then you take the sign. So now you get like a vector, which is either 1 or -1 in every entry, and you multiply by epsilon, so you kind of like throw it to one of the corners of this epsilon box. Cool, okay, so this is the GSM, but there could be many other adversarial examples lying somewhere in this allowed region, and we just have to kind of somehow find them. In a moment, we're going to talk about another better attack, which is called PGD. But let's just finish talking about some visual intuition. So this is actually how it looks like in reality. You have these like regions in this box, which are adversarial regions. So imagine blue is the correct label, but you can get to some other label if you go to some places. And so this is actually I draw it with my own like hand, but you can actually look at like the real examples. This is from one of our papers. So this is how it looks like. So this is a binary classifier on these images, which are like the training set of just dots in 16 2D objects. And you see that the classifier is correct. So there is like 0 training error here, right? So all the dots are correctly labeled. But this is really non-robust model because you could see that almost anywhere, or at least for many samples, you could find adversarial examples in this allowed region, allowed box. Cool. And this is how it looks like after we train it adversarial. Yeah.
So does this imply that the ones that are completely within the box are safe?
Yeah, in this case, you can actually visualize this as long as, okay, there was also like this was the color was generated by sampling many dots in between. So in general, you could think that there is like maybe some adversarial example like isolated somewhere here, but probably not. On some of those you can actually improve this, but not in this one. Yeah, but in this simple case, so this is like the 2D alert. In 2D cases, it's nice to have this 2D toy example. You can actually visualize how your world looks like, and you can just prove by visualizing everything that this model is robust for this training set. Okay, so let's see, but yeah, in general, you cannot know it, and obviously with images, high dimensional objects, it's very hard to make sure that your model is robust.
But if you take a slightly larger epsilon,
right?
You can break again.
Right. So epsilon is a hyperparameter, and you know, now that you are familiar with the like terminology, you could argue whether this like infinity bound is real, like realistic in a sense. You could argue about it for any epsilon. So when I generate like this small perturbation with delta, I can actually change just one pixel in your image, which can be larger than epsilon, but it would still be imperceptible, and you can still get a adversarial. So like, okay, so like a few like philosophical notes before the break. So it's like there's no one definition on what is like perturbation. It's like open to discussion. But in a sense, the scientific community kind of like converged to this definition of robustness for epsilon boxes or balls, depending on the norm, which is easier to like kind of like define and easier to say something about it. Does it apply to realistic settings? Not always, and obviously in general, you get some model and you could find ways to attack it, which are not exactly the way it was defended for. This is not how things work in general. And the bottom line, before we actually continue to think, this problem is far from being solved. Many models, you can very easily break them, and many models which are considered or like claimed to be robust are actually not. Even sometimes not in their own definition. But okay, what's your name? Eden. Okay, Eden asked if why would I care about maybe I'm not sure if that's exactly what you asked, but like why would I care about robustness? So for the moment, it's mostly about privacy. You don't want to publish your model and then someone could like very simply change the label of something. You can think of some examples, but at the moment it's mostly about privacy. We will see some cool properties for robust models which are not necessarily privacy, but I say like this is the main motivation.
What do you mean by privacy?
So why would I care if my model is robust or not? So mostly because I want my model to act as I hoped, as I wanted, like I want my model to act the way I thought it would act. So if I think that my model is good classifying images, and then I give it a pig and telling that it's an airliner, that it doesn't work. So like you can think of like trying to attack your model. Someone, if like you know, here's a very stupid example, but this one comes to mind. You have some you have some application online that I don't know, like take your image like the face of a human and then does something on it, and you don't want it to operate on anything. You only to operate on human faces, and then if you upload the face of a dog, you don't want it to add glasses or do whatever the editing. So maybe you can put a classifier to first classify if this is a dog or a human face, and then according to the answer, then you do the rest of your application. But then it would be very easy to break your model. It would be very easy to just take them like a dog face and then do the adversarial attack on it and make it think that it's a human face. So this is like a privacy issue in general. Which is the main motivation for all this field. Okay, cool. So let's talk about another attack, which is called PGD. It stands for projected gradient descent, or Iterated-GSM. So you will understand in a moment why. Again, if we have FGSM, we only did one step. We ended up somewhere. And the PGD is going to look at this as, okay, we need to find some adversarial example in this region. So let's just try to solve some optimization problem over this whole space and hopefully find something that is better than FGSM, or like maximize this exactly the same loss. Instead of taking just one step, let's take many steps trying to maximize this loss, which would hopefully also be an adversarial example. So there's like a good reason to believe that if the loss is very high, then it would also change the label. Okay, so how does it work? So, okay, we have this like attack model that we discussed before, so we can allow it to be all the deltas which are bounded by some epsilon. And we've seen FGSM, right? So they have like to generate an adversarial example, we take the original image, and we add this delta, which takes the gradient with respect to x. We take the sign and we multiply by epsilon. And we end up with this. Okay, what is PGD? It's going to be an iterative process. So we start with the same image, and then we add one single FGSM step. So this is exactly the same equation for FGSM, only I change here. You have an alpha here instead of epsilon. So remember, epsilon is the largest perturbation that is allowed. But now, instead of taking an epsilon step, which will immediately bring me to the edge, you're going to take the alpha, which is usually smaller than epsilon, maybe like 10 times smaller than epsilon. It's a parameter of the attack. Oops, okay, right? So this is how it's going to end up looking. But now we're not stop here. I will just make another step. So this is just iteratively taking more steps, but now x is going to change. So the gradient with respect to x is going to change. I'm going to make small steps, trying to find some delta which maximizes its loss. And this is how it looks like. So we're adding some small perturbation at each time. And by the end, hopefully we'll find something which is maximizes the loss better and is hopefully a better candidate for being an adversarial example. One more thing. So while we're doing this, we can kind of like drift away from our allowed epsilon. So we just clip it at each step to not be larger than the epsilon. Well, this is PGD or Iterated-GSM. And let's look at the numbers. So again, we've seen this one. Let's add the PGD. Okay, so now we can attack. First, let's try to attack these models, the standard trained model and the FGSM adversarial trained model with PGD, which is a stronger attack. So we see that with the standard training, we managed to find even better adversarial examples, the worse accuracy, and we managed to also kind of like break the adversarial trained model. Okay, what can we do now to defend? Yeah.
In this case, we train the adversarial training with the new example.
This is the same as before. This is the model trained with FGSM. So at each iteration, I get my clean batch and I generate adversarial set using FGSM, which is one step. But now I can take this robust model and attack the test set using PGD, which is much stronger. And then you see that it works better. But what can we do now to defend against PGD?
Train it on PGD.
Exactly. So we can do adversarial training, but with PGD. So at each training step, I get a clean batch. I generate adversarial set using PGD. So I do like many steps, and I get like, hopefully better adversarial examples. And these are the numbers. So this is the test accuracy. This again is slightly less than the standard, but they look better than the FGSM. That's how it is. The FGSM accuracy is now this model is a little bit more robust to FGSM, but it's also more robust to PGD. Okay, and again the question is, did we solve the problem? What do you think? Of course, we can come up with stronger attacks. PGD itself, it's very important, like the parameters. How many steps are we going to do in the iterations? How many iterations? Could be 50, 100, 500. The more iterations you do, the higher the probability that you will find adversarial examples. There are some other like usually you start from like you can do for the same image, you could do iteration, but instead of starting from the image itself, start from some like random perturbation and then do these iterations, and this would also probably make your attack better. So again, these are like stronger attacks for PGD, and in general, you could come up with other attacks. Having said that, these are probably the two most common approaches to generate adversarial examples. So I would be happy if you are familiar with them, and then you can go and read your literature, and you will be familiar with FGSM and PGD. Okay, so now you asked before, what about other data sets? So here are some numbers. For example, for CFAR10, these are not MNIST anymore, these are images, 32 by 32, still rather small, trained with ResNet, standard training, test accuracy can get like 95%, which is nice, it's pretty high. But then PGD with epsilon of this, so each pixel is some number between 0 and 255. So even if we take this kind of like epsilon, which is just 8 steps in like RGB, which is very, very small, you can easily completely break the standard trained model. If we train it with PGD, then you can get to these numbers. So the test accuracy is slightly less, but PGD is it's better, like more robust. Again, you could always ask, did we solve it? Probably not. Probably you could look harder and find better adversarial examples and get to even lower accuracy, even on these models which are trained with PGD. Yeah.
So if you have this like PGD that you apply to it, has anyone considered training a model to look at the input first and see if it has like PGD or PGD attack on it?
I'm not sure I understand the
Like the model will learn how to like see like, oh, like there's like some noise that's been added to the image just by like how the individual thinks about it.
So I think that you're asking, can we find a better way to defend against adversarial examples,
Yeah, but like,
even for adversarial robust models?
yeah, like by like detecting that like the example that's being fed in right now is modified somehow.
The simple answer is there are many suggestions for this, and almost all of them could be broken, so it's very hard. And again, I have some slides, maybe touch on that. Okay, so here are some more numbers. So this is on ImageNet. Again, standard training gets 76%, top, I think 1 accuracy. PGD, again, completely break the model. And if you train it with PGD, then now it's a little bit more robust, but you could hardly argue that this is a good model for classifying images because the test accuracy is now very, very low. In general, there's also like it's an open question whether robust accuracy and clean accuracy are like, is it like a trade-off between them? There is a nice paper that shows for like a specific case that there's actually like there must be trade-off between them. If you want this model to be robust, then you must lose on clean accuracy. But this is like a very I don't know, like a toyish example. It's really nice, but still not very realistic. In general, it's not clear, but you do see that. And when you try to train adversarially, you lose on clean accuracy. Okay, cool. So okay. So we've seen FGSM and PGD, and someone of you already mentioned that in order for this to work, you need to know the model itself. You need to compute the gradient. So this is called white box attacks because you know all the model, you know everything about the model. So let's talk about black box attacks. What is it? So in the white box setting, I have some clean image and I can generate an adversarial example by taking the gradient as we've just seen. But what happens? Okay, what happens if I don't have the model? If I only have access to the model, like this example that I told you about, actually that's like something that I thought of trying. So we have this like if you're familiar with MyHeritage, it's really cool. They have this like really cool image applications, amazing. One of them called Deep Nostalgia. You can upload the face of someone, and then you can get it to like a talk and something like that. And then I thought, okay, what if I would upload like an image face of a cat or a dog? Would it like make it speak just for the fun of it? And it would not allow you to do this. So kind of like they probably have something that checks whether this face is of a human or not. And I didn't manage to do it, but I thought it wouldn't be really nice to try and break this. And so this is like an example of a black box attack. I have no idea what is going on in the servers of MyHeritage. I can feed images and get the outputs, but I cannot get gradients. I have no idea what's going on in general. Yeah. So this is a black box attack. What can we do? in order to generate adversarial examples for black box model. Right, so I cannot get the gradient. Okay. Okay, any ideas, by the way? Right, so now I have a black box model. What can I do? Okay, so there, okay.
Yes.
Hmm?
One is trying to get the gradients like by perturbating.
But for numerically, they just feed a lot of images and try to like get the
Yeah.
that's one way. Okay, but yeah.
The other, you can try and build a network yourself. And
Right.
if it's part of the data, like in this part, you would.
Are you familiar with this or okay? So because this is what I'm going to show. There's one note about why it's a problem to numerically like find the gradient to estimate. It takes a lot of time, right? So you will not be probably able to upload if your image is even small image 256 by 256, then to estimate the gradient you need to check in each direction, like 200,000 samples, and yeah, it would not be very realistic to try. Okay, but sorry. Elad. So again, this is what Elad actually was saying. This is the common way to do with black box. So I don't know the model. I have no idea what it is, but maybe I know that it was trained on some familiar, very famous training set from the internet, ImageNet, or I don't know. So I will just define my own network, and I will train my own network on this training set that I hope this model was trained on. And now once I have my own model, then I can generate adversarial examples by having have access to the gradients and I can do whatever I want. So now I can take these adversarial examples that was generated by my own model and check if this works for this black box model. And the question is, yeah, will it break? Okay, so let's talk about a very intriguing property of adversarial examples called the transferability of adversarial examples. And this is some numbers by these guys over here. They trained several models, different model architectures on ImageNet. And after doing that, yeah, they got a pretty good top 5 accuracy on ImageNet, right? So they present 50, 101, and they all get 90%-ish accuracy, which is very good. And now they took just one of them. So let's just take this one and check what is the accuracy on the FGSM attack. And you see that it can break the model. Not surprisingly, we've seen that it is work. But what if we take these examples that were generated from this model and then just take this example and feed them to the other models? What would happen? And this is what happened. So these adversarial examples that were generated on ResNet 152 managed to also break the other models, which is pretty cool. So it kind of tells us that we can transfer adversarial examples from one model to another. And if you can do the whole like two-way thing. So this is like generating FGSM attack on the same model. And you can see that it managed to break. So this is not surprising. We've seen this already. Doing FGSM attack on resonance 50 and feeding it to resonance 50, and this breaks this model. But what if we then feed it to the other ways? So you see that in all cases, adversarial examples generated from one model, then fed to another one, were able to break other models, sometimes to better, sometimes to worse. And this is only FGSM. Could do the same with PGD, and you get even worse results here. And the idea is that adversarial examples actually transfer from one model to another. We could. This is like a good motivation why to do these suggestions that we did for black box attacks. Possible reason why it works. So this is a nice suggestion by Ian Goodfellow. We show this here. So he trained just like logistic regression on these kind of images to classify between 3 and 0, 3s and 7s. just linear, right? Linear model, logistic regression, you train it, and then you can look, this is a linear model, so it's in the same shape as the inputs. So you can actually visualize these weights. This is how it looks like. And then he did the same thing again, starting from another random initialization, and he ended up with this. So, and you can see that the features that the model learned was almost the same. So even though there are both different models that were trained differently, so different initializations, they kind of converge to learn the same features to separate between 3 and zeros. So it would not be very surprising that images that fool this model would also fool that one. So this is like an intuition why the transferability works. And this was kind of later somehow generalized to more realistic settings in this really nice work. And they suggest that adversarial examples actually come from the data itself, not from the model. So it's like in the data, if you have something like here's like a very simple example. Say all your cats in your training set have like the upper left pixel is blue in all the images of the cats, and the dogs do not have this. So now I can very easily take an image of a cat or take an image of a dog, paint the upper left pixel as blue, and my model would probably classify this image as a cat. And this property comes from the data, not from anything like the architecture or something like that. Okay, so this is an intuition why it works. Questions so far?
Like in theory, you could attack training data too.
Yeah. There is a lot of works on trying to like attack from the data perspective, like poisoning the data, or there's a nice works on unlearnable data sets. If you can add some perturbations to your data to make it like the other will not be able to learn from that. Then there are other works which like break unlearnable. It's nice. It's nice field. Yeah. Okay. So let's make like a philosophical break for a moment. Yeah.
What was the difference between
This one?
No,
I think it's the same. I think it's the same. I don't know why I put it twice. It should be the same. Same data.
No, the data is the same, but you have like two other configurations, and then you
you train a linear model.
Right.
So you train just one like vector, basically, as a classified. And you do it twice. So you initialize it with some random initialization, then you initialize it some else, and then you just train using logistic regression loss. But the data is the same. Okay, so it's like philosophical thinking of adversarial examples and having like the bigger picture. Is it really surprising that we can fool neural networks? So it was very surprising back in the day, like 2013, 14, when it was out, like people were really surprised by that, because neural networks were so good at classification that they kind of like hope that they will, I don't know, be also good otherwise. And then you show that you can really easily break these. So like the goal of AI machine learning is kind of like build something which is similar to a human being. And then if you can show that these models are so easily break, then they're still really far from achieving this goal. And in this sense, also not so very surprising, because do you really believe that neural network are the same as human? We probably have some more steps to go. If you think it from this perspective, it's not so surprising, but it's still pretty cool. So you could, I don't know, like look at it as if you can classify everything in the world. Of course, it's not really true, right? But let's say you can classify everything, and the human can be correct on some of it, and then machines like neural networks can also be very good on the stuff that humans are, but also very good on stuff that humans are not. So that's also like I don't know if you've seen it, there's like this nice example on how they're comparing the classifiers, image classifiers, like VGG, resonance, stuff like that. There's like this experiment done by Andre Kaparti that he trained himself on ImageNet. and he managed to get 5% error on ImageNet, but then modern neural networks can get lower than this. So yeah, like if you ask human to classify between certain types of birds, probably, unless you're like or ornithologist, I'm not sure to say the right word, you will probably fail. But the machine can learn this stuff, okay? But yeah, we can very easily break this by perturbing it and adding some noise, which is completely like maybe correlated with some features in the data that are not will not be like really aligned with the true classes. So that's what I've shown. I'll skip that. I want to get to some more interesting place. And also like the bigger picture of fooling models. There's a lot of ways, a lot of things to explore in this area. There's a nice blog post by guys from Microsoft that kind of like divide this world for like intentionally motivated failures and unintended failures. So in intentionally motivated failures, you get all these like perturbation attack, a poisoning attack, you poison the data. There's like nice adversarial examples in the physical domain. So even if you don't have like direct access to your model by feeding tensors, if I have my model on my phone and I can also only have access through the camera, you can still fool classifiers. It's pretty cool. Maybe if I have time, I'll show you this in the end. So these are all intentionally motivated failure cases of models, but you have many other unintended failures like distribution shifts or corruptions that you were not thinking of. And from all these bunch of many cases that could fool of the failure cases of machine learning algorithms, we only discussed this one here, perturbation attack, which is also many people have, like many of you asked me like why epsilon, why is this norm? Like I said, there's like no one way to define how a model would fail, but the research community kind of like converged this definition of smallness, which is bounded in infinity norm, because it's easier to prove or do things. But this is the bigger picture. Cool. Okay, so remember the bigger picture. Yeah, so it is like hard to attack. Sometimes it's pretty simple, but sometimes there are like suggestions on how to models robust, and then you will probably have to like think a little bit more on how to attack these models. It's not very straightforward, but it is much harder to defend because you somehow need to prove that there are no adversarial examples in all the box. Right? So I stress this, you need to prove. In most cases, actually there is like one work that I'm aware of that's actually like proved that they are robust for some epsilons, but these epsilons are really, really small. It is not realistic at all. What you would usually do, or maybe prove that it is very hard to find adversarial examples. What you would usually do is need to evaluate. So evaluation for robustness is again also a hard open problem in this field. And it may sometimes be very tricky. So usually you would take like PGD with many steps and you would really try hard, maybe black box attacks on your model, or maybe come up with some creative ideas on how to attack your model. And I want to give you like one example why black box attacks are very important for evaluation. So we've discussed black box attacks, but only in the aspect of like attacking some model you don't know. But black box adversarial examples are actually very good at evaluating your model. And this is a true story. So here is an example. Again, these numbers that you are familiar already with. So we have like the different models. You have a standard model, some known robust model, and then some new model that we try to build and to make it robust. And then we want to evaluate how well it acts. So here is the standard accuracy. So the clean model gets like pretty good accuracy. the famous robust model got this accuracy, which is a little bit lower, but still quite good. And we got this accuracy here, which is, it's okay. And then we said, okay, let's see if our model is actually robust. So PGD and the standard model is very easy to break. The best known model got this number here, 53%, and we got that. So 79% accuracy on PGD, which is like, oh my God, it's like it should be like win the best paper award on NeurIPS, right? Because we managed to get like a robust model, which is much better than the previous best one. Are you okay with the numbers? Do you get like the point? Okay. So what went wrong here? And it took us some time to figure this out. We didn't evaluate the model correctly. So we did PGD. We used the true PGD on our model. But actually, our model was not generally robust. It was robust for PGD attacks. So, which means that we did not evaluate. And maybe I can show you why and how it is related to black box. Yeah. So instead of just looking at the numbers, you could look at the adversarial examples that were generated. This is again, I don't know, telling you from my own sad experience. When you're working with numbers, sometimes it's very hard to understand if this is true or not, and it's always good to kind of like check if you can visualize some things. So in this case, you can visualize the adversarial examples themselves. So these are the clean images, and these are the adversarial examples on the standard model. So we've seen these ones already. This fooled the standard model to completely broken. And these were adversarial examples generated on this famous robust model. So you see that these are already a little bit different. And it's interesting because kind of like in order to generate good adversarial examples for robust model, you really need to change the important features in the image. So for standard model, it was enough to change these pixels here, and then you immediately get like completely different numbers. But when you train on these images, then it would be harder to find. And this is how it looks like. So this is how good adversarial examples should look like. And when I looked on the adversarial examples generated from our model, this is what I've seen. And like, what is going on in here? So some of them barely changed anything. And then here we actually got something that looks like standard model. And I don't have the numbers, but when we fed to our model these adversarial examples here, it completely broke our model. So, which means that our model was not robust. It just fooled PGD. This is not exactly what happened, but if you want like a very simple way to completely break PGD, take the outputs of your model and multiply them, the classifier, just multiply them with some really large number. So you have the output model, and then you multiply it by 10 to the power of 20. Would it change your classifier? No, right? Because the maximal prediction would still be the same. So it would not change at all your classifier. But what would it do? So when we run PGD, we take the gradient with respect to the loss. And this cross entropy loss has this softmax. And when you multiply your logits by a very large number, the probabilities would be either 1 or zeros everywhere, which means that the gradients that would flow back to the input would be nothing. It would not pass this softmax. So this is that's what actually happened here. So for some images, we didn't get any gradients at all. And for the ones that we did get, the adversarial examples were actually very similar to standard model, which means that we were not robust at all. And this is very common in this literature. There are a lot of papers claiming to be robust, and very easily you could fool them. And the one way to check, evaluate this is actually using black box attacks from known robust models, because these generate like true or better adversarial examples. Okay. Cool. So we are kind of like finished with the security part of those examples, and in the last few minutes, I want to show you some nice properties. Actually surprising advantages on the adversarial examples. And let's go back to these examples of appeal. Right, to remember all this. Here is Python. We'll put it in the first slide. Okay. So you can follow this gradient, right? That's what you do. We follow the gradient with respect to x or the model. By the way, are you okay with the temperature here? Yeah, okay. I see you following the station. Okay, I know. Cool. So what happens if we try to follow the gradient, but not of some model, but of robust model, which is very similar to what we've just seen? What would happen? So here is an example. So of doing this example, following the gradient with vector x, once for standard trained model, once for a robust model. These are two images, like there's a primate and the bird here. And if we follow the gradient of standard model, then we get this noise, and we manage to fool this classifier to think this is a dog and this is a turtle. But we didn't really change the image itself. What would happen if you're going to do the same with robust model? So this is a L infinity trained robust model. And in order to change the label from primate to a dog, when following the gradient, it really had to change the image itself. So it, like we've seen with MNIST, it had to generate the perceptually, semantically meaningful changes to the image. And this is what happens with the dog. So in order to change the bird to a dog, it really had to change the image to dog, which also kind of say, okay, but is it really the examples or not? And by the way, if you do the same with L2 trained models, so robust not in L infinity, but in L2, you get smoother stuff, which is pretty cool. So this tells us, or at least that's right, the consequence of this. If you train your model to be robust, then it also has to be more aligned with the semantic meaning of your class. So this is why it's very good to one motivation to why it's good to train your model robustly. Another issue is it takes a lot of time. So just think of PGD. You want to train robust model with PGD with 50 steps. So now instead of having one step for each batch, it's going to be 50 steps for each step. The training time is going to be multiplied by 50, which is not nice. Okay, cool. So this was actually used to show that you can kind of like do stuff with robust classifiers. You really need paper, image synthesis with a single robust classifier to show they can actually generate images from a robust classifier of different dog, parent, stuff like that. This is that. Okay, and one last thing before we say goodbye. So until here, these are all stuff that kind of the community knew till this is from 2019. Could argue this is a quite long time ago. And now we are living in the era of LLMs, the large language models, and you can ask, okay, does all this hold to language models? And I want to show you an example, not on pure language models like ChatGPT and stuff like that all of you are familiar with, because we will need some more time for that, but there actually exist attacks on ChatGPT. I don't know if you've seen this, it was kind of popular media. You could find like, if you ask your model how to build a bomb, something like ChatGPT could tell you as an AI model, I am not allowed to tell you about this, but you could find like suffixes that you add, the completely nonsense characters, which would jailbreak the system, and then it will tell you how to build the bomb. I will not go into this, even though it is quite similar to the method that we've seen, but it would require some more time. I want to show you how it works with vision language models. So what are vision language models? So here's an example of Mini GPT-4, which is a vision language model. So it can get as input both text, but also an image. You could also do it with GPT-4. And it would say something about it. But then you could think of language models are actually classifiers, because I think you will learn about it in the next lessons. But roughly speaking, a language model is something that gets as input a bunch of words, and it needs to predict the next word from all of the possible words, which is a classifier. If it's a classifier, you can break it as you break classifiers, as we've seen with PGD. So in a very nice, can we actually break it? So in a very nice paper by these guys, what they did is just do PGD on the image that you feed into your model in order to, again, maximize something. So what did they want to maximize? They want to maximize the next predicted word will be some offensive word. And while doing this, they managed to do this. So it's like like offensive content. So if you don't want to look, that's like what he generated, describe this image, and you get this like, yeah. This ugly hag is wearing a green hood and carrying a basket of apples. Blah blah blah. There are even worse examples. So you can look it up in the paper. I didn't want to put it on the board, but really, it's you could get your model to say very nasty things just by playing PGT on your image. Okay, and I will end by that. So what have we learned today? So we've seen some adversarial examples. That's what they are. We learned about FGSM and PGD, which are probably the most common attack methods. We learned a little bit on adversarial training and black box attacks, and we've seen some cool results. And yeah, that's a broad research topic, which is very open. Definitely now with all the language models that are coming to be very popular. And yeah, thank you. So next Wednesday, I'm gonna have Shai explaining you about stuff that you need to know in order to understand language models. Thanks. Thank you for your time.